So this idea of completing the square is quite an important idea that we need to know. Most commonly we see it with solving quadratic equations. It does have other uses as well, the idea. So here's our quadratic, and all right, this one can be factorised, but I'm using it as an example of completing the square. So let's pretend. Oh, factorised? No, don't know how to do that. So we're going to use the technique of completing the square. The same steps are involved every single time. The first step is to move the constant. So I've moved 7 over to the other side. So the first step, move the constant. Now the idea now is to make a perfect square on the left-hand side. And so what I do is add half the coefficient of x squared. Not half the coefficient of x squared, but half the coefficient of x squared. The pause is very important. So the coefficient of x there is 6, half of that is 3. 3 squared is of course 9. But that creates on the left-hand side a perfect square. And so it will factorise to be x plus 3 all squared. And so we're saying something squared is equal to 16. Well, that must be either plus or minus 4. I can move the 3 over, and there's my answer, negative 3 plus or minus 4. So my two possibilities, negative 7 and 1. So that's the idea of completing the square. Create a perfect square. This now allows us to create that quadratic formula. Because I can generalise the quadratic equation, ax squared plus bx plus c. If I solve this by completing the square, mind you, the first thing I'm going to do is divide everything by a, because when I complete the square, I like it to be a monic rather than ax squared. So divide everything by a. So all right, first step was move the constant to the right-hand side. So that becomes minus c on a on the right-hand side. We then said add half the coefficient of x squared. Well, the coefficient of x here is b on a. So half of that would be b on 2a. Square it, we'll get b squared on 4a. So square it, and there we are. That creates a perfect square on the left-hand side. So I know x plus b on 2a all squared is that lovely expression on the right. But it would look a lot neater if it was just one fraction. The common denominator will be 4a squared. Whoa, have a look at the top. That looks familiar. Now becomes b squared minus 4ac. Okay, well something squared equals that. Therefore, x plus b on a must equal plus or minus the square root of the right-hand side. Square root of 4a squared being 2a. Move the b on 2a over. There's our quadratic formula. So as I say, someone said, well, hang on, you do those steps every single time, so therefore, why don't we just use this formula rather than having to go through that every single time? Let's have a look at another one here. Another way of completing the square, if I had to solve this, x squared minus 6x plus 6 is equal to 0. I could complete the square by thinking this way. I know half the coefficient of x there is negative 3. So I know that when I complete the square, I would get x minus 3 all squared. Problem is, when I expand out x minus 3 all squared, I don't get 6. I get 9. So therefore, to get it back to 6, I have to subtract 3. What I now have is the difference of two squares. I have x minus 3 all squared minus the square root of 3 all squared. So I could now factorise that to be x minus 3 plus root 3, x minus 3 minus root 3. So therefore, x is either 3 minus root 3 or 3 plus root 3. So there's an alternative way of completing the square to get the answer. It might even be a little bit quicker, and I think it's a little bit neater by using difference of two squares. I don't know whether you've seen that way of doing it before or not, but there you go. All right, everyone, put their left hand over their left eye. What are you left with? One eye. Okay.